1.
Hello, my name is William Terry. I'm an undergraduate mathematics and physics major at Cal State Fullerton. And I'm here to talk about my research on quotients of matrix spaces, advised by Dr. Alfonso Agnew and Dr. Matt Rathbun. Previous researchers quotiented complex 2x2 matrix space by GL2C. Using this as a foundation, the purpose of this research is to see what happens when we quotient out by different subgroups. Mathematics is a complicated, multi-layered, time-consuming process. This work aims to summarize the many proofs and long hours involved. To start, I'm going to give some background on topology and quotients. Topology is an area of mathematics that studies the properties of spaces that are unaffected by continuous deformations. Consider a square and a circle. Geometrically, these are different shapes. But if you were to sort of round out the corners and curve out the edges, you could morph the square into the circle, what's called continuously. That is, without breaking or twisting the shape. Topology studies processes like this in a rigorous way. A topology on a set uses open sets to relate points. Open sets are generalizations of open intervals on the real number line. So for example, all the points between but not including -1 and +1. Two spaces are then topologically equivalent when there is a one-to-one correspondence between both the points and the open sets. Since one could be continuously morphed into the other, the square and the circle from earlier are topologically equivalent. Topology is useful for the following reasons. First, it allows us to consider similarities in geometrically different spaces. The square and the circle are geometrically different, but they have some similar properties that topology allows us to study without having to account for the geometry. Second, topology allows us to think of complicated spaces in terms of simpler equivalent spaces. Suppose you have math that's difficult to do around corners. Well, since the circle is equivalent, you could do your math on the circle instead and avoid corners entirely. And third, topology facilitates gauging closeness in a space with no measure of distance. What does close mean in a space where rulers don't work? Well, topology allows us to answer this question in a rigorous way. One way of generating a topology is through a quotient. A quotient is a way of gluing parts of a space together to create a new space. Points are grouped into equivalence classes, which become the points in the new quotient space. And an equivalence relation is an instruction on how to group these points together. Consider a ball pit along with a collection of boxes. Here, the ball pit is our starting space, and the boxes form our equivalence classes. If I were to organize the balls by, say, color, and then place them into boxes, then I've defined an equivalence relation on the balls, and the boxes become the points in our new quotient space. Bringing this all together, two matrices are considered equivalent if and only if they are subgroup multiples of each other. We use the subgroups GL2C, SL2C, U2, and SU2, which are interesting and well-known objects that are widely used in math and physics. Each of these subgroups progressively gets smaller, and as we'll see, the topological properties of the quotient space will change qualitatively. Choosing to quotient out by GL, SL, U, or SU would be like in the ball pit example, choosing to separate the balls by color or by age or maybe by level of damage. This diagram forms a template of ones that we will see on the following slides. We start off with complex 2x2 matrix space. This pie map denotes the process of taking the quotient, which leads us to our quotient space in this fractional notation here. We then establish a topological equivalence through this p map to a more intuitive space that's easier to study and comprehend. We start with some foundational results, the GL2C quotient. Here, previous researchers separated complex 2x2 matrix space into invertible and non-invertible matrices. The invertible matrices collapse to a single dense point, which is dense because it's easy to nudge a non-invertible matrix into an invertible one. The non-invertible matrix equivalence classes are only distinguishable by a direction vector, and so we get a sphere. This quotient space is then the sphere along with this dense point, which is non-Hausdorff because every open set contains the dense point. Consider a piece of paper with two distinct points drawn on it. No matter how close together these points are drawn, it's always possible to draw circles around them so that the circles don't touch. It may take an incredibly small pencil and a microscope, but it's always possible. This is a property of a Hausdorff space. Our space, though, is non-Hausdorff, which means it's not always possible to find circles that don't touch. It should be noted that non-Hausdorffness is sort of an odd property. Even topologists don't work with it very often because it's non-intuitive, though it comes out naturally from our quotients. Each of these images depicts the GL quotient space. As you can see in picture A, circles around points P and Q necessarily contain the dense point star. Picture B shows the same idea, with a single sphere being continuously pinched by a point, more so emphasizing that this point is close to other points on the sphere. Even if you were to move points P and Q on opposite ends of the sphere, as far apart as they can be, they're still in a sense close to each other because they're both close to the point star. Another way to think about this space is like images of the Earth from outer space, where the Earth is the sphere and the cloud layer over the top sort of acts as a dense point. The first new original result is the SL2C quotient. As in the GL case, we separate complex 2x2 matrix space into invertible and non-invertible matrices. The invertible matrices give the complex plane without the origin, while the non-invertible matrices once again give us a sphere. This space, the sphere at the origin of the complex plane, is once again non-Hausdorff, now because every open set in the sphere bleeds into the complex plane and intersects. This is sort of a different non-Hausdorff behavior than before, though. In this case, it's localized around the origin, whereas in the GL case, it was non-Hausdorff everywhere. As you can see in picture A, circles around points P and Q cross over into the plane as concentric disks around the origin, so they intersect, and in the space as a whole, points P and Q are close. But if you were to find a point R that's far away from the origin, it's still far away from points P and Q. And image B shows the same idea, with a single sphere being continuously pinched by the plane, emphasizing that the sphere is at the center of the plane. The next new original result is the U2 quotient. Unlike in the GL and SL cases, we can actually consider invertible and non-invertible matrices together. Equivalence classes are identified with Hermitianized products, AA star, which are positive semi-definite. In relativity theory, the causal future for an observer, which can be thought of as everything you can interact with, directly or indirectly, also corresponds to positive semi-definite Hermitian matrices. And so our quotient space is the causal future, which is a Hausdorff space. This image depicts a lower dimensional analog of the causal future in spacetime, where these bottom axes represent the spatial coordinates, and this vertical axis represents the time coordinates. This blue cone is the light cone, and it corresponds to the non-invertible matrices, while the red interior is everything that you could directly interact with, and it corresponds to invertible matrices. The final new original result is the SU2 quotient. Similar in the U2 case, we can actually consider invertible and non-invertible matrices at the same time. Equivalence classes are identified with a Hermitianized matrix AA star, along with the determinant value satisfying this equation. The quotient space is then the causal future, but now with a circle attached to each point inside the light cone, and it's still a Hausdorff space. You can see once again we get this blue cone, but now on the red points on the interior, we have circles attached to them with radii depending on how far away from the origin they are. To summarize the key results, the SL2 quotient topology has the property that points that are far apart on the sphere are close in the space as a whole. In physics, quantum non-locality is a property of entangled particles that no matter how far apart they are, interaction with one has a direct effect on the other. So despite being far apart in our universe, entangled particles are in a sense close enough to interact. Perhaps the SL2C quotient topology could be a significant tool for modeling this sort of quantum behavior. Also, the U2 and SU2 quotients are both fundamental objects from relativity theory. The fact that both of these represent fundamental physics further suggests that the SL quotient should also. To conclude, the SL2C quotient gives interesting non-Hausdorff space. And this space has properties that are similar to quantum non-locality, while the U2 and the SU2 quotients give interesting Hausdorff spaces that are intimately related to relativity theory. As you quotient out by smaller subgroups, the separation properties become more recognizable and your topologies become nicer. We've also studied these properties over the real numbers, which have similar properties with reduced dimensionality in the quotient space. Thank you for listening to my talk, and I look forward to your questions.